So now that we have the language of boundaries of surfaces at our disposal, we can properly state Stokes' theorem. Let's remind ourselves about the curl operator, which is one of the important ingredients into the statement of the theorem. The curl of a vector field is what we call a symbolic cross product. So to take the curl of a vector field, the way that I like to remember this is we take the del operator and cross it with the vector field. So we put the symbols E1, E2, E3 into the first row of a 3x3 matrix. And of course, these symbols are meant to represent the three columns of the 3x3 identity matrix. Then we insert the del operator, whose coordinates are partial sub x, partial sub y, partial sub z. And then we insert the coordinates of the vector field. Here we're calling them f1, f2, f3. And when we take this cross product, we end up with a vector in R3 whose coordinates are given by various differences between partial derivatives of coordinates of the vector field with respect to the variables. And it's important to remember that the curl of a vector field is a new vector field. And how do we interpret the curl of a vector field? Well, for me, it's always useful to remember the notion of torque. One way I like to think of torque is as some sort of rotational force in space. And torque is given by the vector quantity of the distance from a particle to an axis of rotation crossed with the force vector. So here, since curl is given by the cross of the del operator with the vector field, the way that I like to think of interpreting curl is as some sort of instantaneous torque or infinitesimal torque. So the idea here is that curl measures the propensity of a vector field to produce rotation at a point. So the idea here is that if we take the curl and plug in a point, the curl points in the direction that would produce maximal counterclockwise rotation within the vector field. So what is Stokes' theorem? Well, much like Green's theorem, informally, what Stokes' theorem says is that if we integrate the curl of a vector field, what we should be doing over the surface is measuring the propensity or the density of rotation throughout that surface. And that should be the same thing as calculating the circulation of that vector field around the surface. So rigorously, the statement of Stokes' theorem says that the surface integral of the curl of a vector field is the same thing as the circulation of that vector field on the boundary of the surface. Or the double integral over the surface of the curl of a vector field dotted with d bold vector s is the same thing as the line integral of that vector field over the boundary of the surface. And just like whenever there is a statement of a theorem like this, it helps me to track the units in order to make sense of the statement. So here I accidentally called this theorem Green's theorem because sometimes I like to make analogies from Stokes' theorem to Green's theorem. This should actually say Stokes' theorem. So tracking units helps us make sense of Stokes' theorem. So what are the units on curl? Well, if we pay attention to any of the coordinates in curl, we realize that we're taking derivatives of the coordinates of the original vector field with respect to the input variables. So here we should end up with force units per distance unit. And in a surface integral, the d vector s quantity has units given by distance squared. So when we multiply force over distance by distance squared, we get force times distance. This is compatible with our interpretation of circulation integrals, which is the vector line integral of our vector field over the boundary of our, and this should say partial s, not partial d, over the boundary of our surface. The units on f are force units, and the units on d vector s are distance units. And when we multiply those together, we get force times distance, which is exactly the units for circulation.